Okay. Okay, so the object of today's class is to figure out all the trig identities. Okay, so all the trigonometric identities that you learned in high school that you really need to know for calculus. So we're gonna sort of invent them, okay, or discover them from this circle, okay, which is the unit circle. Again, this is 1, 1, minus 1, minus 1. So this is a circle centered at the origin with a radius of 1 of the Cartesian plane, okay? So like I did last time, okay, I'm going to redo it. I drew a certain angle, okay, starting from, so relative to the positive side of the x-axis, okay? So I'm drawing an angle, a radius right here, okay, which is open at an angle. So I'm going to call this angle theta, okay? Or let's call it x. Let's just call it x, okay? It's okay. And what's very important for me is the coordinates of this point here. They're important for me, okay? So if I draw a straight line, vertical line like this, okay? This height here, this height is exactly the y coordinate of this point. And this length here is the x coordinate of this point. Make sense? Okay, so that's the x, y. Okay, so let's put in some measures. This, of course, is how much? From here to here. How much is that?
1.
1.
1, perfect. Obviously, because that's a radius. And from here to here, we said last time, it's called the cosine, right? Remember? This is called the cosine of x. And this height here is called the sine of x, right? You remember this? I think we said this last time. Sine of x. Okay. Then what I'm going to do is I'm going to draw a tangent to the circle at point 1, 0. So right here, okay? And I'm going to extend the radius until it crosses the tangent line. Okay, you with me? So let me just make it cleaner. So this height now is called the, remember? I showed you last time, I think. Did I show you this one?
Tangent?
Yeah, this is called the tangent of x. Okay, so as you see, it's always of x, of x, of x, meaning that this value, these values here depend on x. Okay, so if, of course, if x, the angle x, instead of being like this, it was like this. So as you see, the cosine would have been smaller, the sine would have been bigger, and the tangent would have been bigger. Okay, so depending on the different angle, we get different values, the blue, the red, and the purple. Okay, so if I study 2 seconds, if I go at 90 degrees, right, how much is the tangent? Where does it cross the tangent? It never crosses, right? It never crosses the tangent because it's parallel. Okay, so that's why I think I showed you this last time, is if you go 90 degrees tangent, you see error. Okay, obviously, because it doesn't cross it. You're asking the calculator, where does it cross the tangent, and it tells you it doesn't cross it. Okay, so it says error. So far, so good? Okay, and I said that there was this measure here. So the extended radius. Okay, you remember how we call this? What is this called?
Secant.
The secant of x. Good. And then, did we finish the whole circle last time? Did we draw everything on the circle? I don't remember.
I think so.
You think so? Okay, so it's good to review. Okay, it doesn't hurt to see it again. So what I'm going to do now is I'm going to draw a tangent on the top, so at point 0, 1. And I'm going to extend the radius until it crosses the upper tangent. Okay, and so I see that it crosses it right here. This is my intersection point. Okay, and this line on top has a name. You remember it? What do you call this?
The cotangent.
Very nice. So this is called the cotangent of x. Okay. And the last thing, the last measure of this, last measurement on the circle is the extended, fully extended radius all the way until it crosses the cotangent, right? The upper tangent. This is going to be this measure here, all the way until here. How do we call this one?
The cosecant.
Very nice. Okay, so this is the cosecant of x. Okay, good. Any questions on the definitions that I gave you? I'm just giving you definitions. Okay, so these are measurements that that come about when you open a certain angle x. Okay, all the measurements I could find. Okay, so every point here, oops, every point on the circle here has a coordinate cos x sine x. Okay, so it's very useful now what we did last class, which is finding all of the important points, right? If you remember, you had for pi over 6, for example, which is 30 degrees, we had the point √3/2, 1/2. So this means, okay, I'm just gonna take the paper 1 second. Okay, so here, that's what we did last class. Okay, if you see, so at 30 degrees, pi over 6, the point was √3/2, 1/2, means that the cosine of 30 degrees or pi over 6 is √3/2, and the sine is 1/2. And that's how your calculator is programmed, right? So 30 degrees sine, you get 0.5, okay, which is exactly the 0.5 here. Okay, you with me? Okay, and which is this length here, the red length here when this is 30 degrees. Okay, who's got questions? Okay, so now let's advance. Okay, so this we did, I think, last time. So now we're going to go a bit further. First thing, can you tell me what this angle is? How much is this angle?
45.
How much?
45.
Oh, no, I don't know. Do you have a protractor? I don't have a protractor. I don't know how much.
There's a 90-degree angle there, so.
This is 90 degrees, okay. And then?
Okay. They don't
Isn't it the same as the angle? Like
Here.
the little angle?
This one? That's what you're saying?
Yeah.
Very good. It's x. Whatever that is, this is. Okay, so I don't know if this, I don't know if it looks like 45 degrees. I don't think so. It looks like maybe a 35 or something. I don't know. Okay, but whatever that is, this is. Okay, you understand, Zach? Okay, so why is this the same as this? Can you tell me why?
Because they're like, I don't know what the word is called, but like.
Well, that's what I'm looking for, the word. I know you know why, but what's the word? You remember this? If you could say it in French if you want. You learned it in French.
No, I don't even know it in French. I learned it in English.
Okay.
But it's like
Right-handed
opposite angles
angles?
on different sides have to be the same.
Is it ulterior,
Okay, you're close.
interior alternate, or what Marcus da Costa said?
Okay, perfect. Okay, so Marcus, I see it on the chat. Yeah, it's alternate interior. Okay, so alternate. So alternate, if you remember, when you had two parallel lines that are crossed by a secant, okay, it's funny, we call this a secant, you see? So when you have two parallel lines crossed by the secant, okay, well, these angles, this one and this one, are called alternate interior. So alternate because they alternate with respect to the secant. So one is on the left of the secant, one is on the bottom or on the right. And interior because they're inside the two parallels. Okay, so they're inside the two parallels and they alternate with respect to the secant. So they're alternate interior. Okay, and there's the alternate exterior, which it's we don't have it here. Okay, it's clear? Okay, now when the two lines are parallel, the alternate interiors are congruent. Okay, means they have the same measure. That's why we could confirm here that this is x as well, because we know that this is parallel to this. Any questions? Okay. So now let's go. I see here, so let's start to conclude stuff, okay? Start to put some, extract the juice from this picture, okay? So I see three triangles here, okay? So one, the small one, then the bigger one here with the tangent, and then the bigger here, upside down one, which is with the cotangent. That's three triangles. So I'm going to draw the three triangles separately here on the bottom. Okay, I'm going to isolate them so that we could work on them a bit, okay, and see what we could conclude from this. So let me just redraw them here. Okay, so I'm going to separate the page here. Okay, so let me see. Okay, I think I went too big. It's okay, I'll manage. And so let me see. No, I think I went a bit too big. Let's just make it a bit smaller. Or else it won't fit. Okay. So that's my small triangle. That's my bigger triangle here. And the biggest one, which is the upside down one. Okay, more or less. Okay, let me just, so, okay, I think you could you see all triangles and the circle? You could see everything? So you see this on top, the cotangent, you could see this, and you could see the triangles on the bottom, yeah?
Yeah.
Good, okay, so I want you to be able to see everything on the screen.
It's a little cut off on the bottom, the triangles.
And now?
That's like perfect.
Perfect, and you could see the cotangent on top and everything? Okay,
Yeah.
good. Okay, so what I'm going to do now is I'm going to label all the values that I know, okay, for each triangle. So let's do a little exercise. So this is right away I could say that this is the angle the angle, they're all x's. So this is x, this is x, this is x, I know, this is 90 degrees, I know, 90 degrees, 90 degrees. That's first thing. True? Then let's go for the small triangle. Let's work on this one. So this measure here is, it's the red line here. So this is equal to, this measures how much? Sine x, right? Okay. The bottom here measures cosine. And the line here is, we said 1, right? So I just drew this little triangle here. It's right here. Any questions? Okay, let's go with this one here. So this line was, I think, purple. So here, this measures, this is tangent. Oops. Okay, this is tangent of x. The bottom here is how much? How much is the bottom here?
It's √3/2.
What?
It's √3/2.
I don't know who said that.
Evan.
Evan, why is it √3/2? How do you know?
Because didn't you draw the oh right, that's true. I'm looking at something else. Sorry.
Okay, so it's very good. Michael, I see you wrote, it's 1. This is 1 because it's from the origin until the edge of the circle. Okay, so this is the radius as well. So that's 1. Good. And this one here, the hypotenuse of this triangle is how much? If you look at the picture, this triangle here. So from here to here is equal to secant of x. Is that okay? You get it? Who has questions? No questions, I could move on. Last triangle, let's go. Let's fill in the blanks. So the top is, this is the cotangent. Okay, then, oops, again. How much is the hypotenuse here?
Cosecant x.
Cosecant x, very good. And the height here is how much?
1.
Perfect. It's 1 because also this is from the origin until here. It's a radius. Any questions? Okay, so let's move on. So now let's see what we can conclude from these 3 triangles here. Okay, so the first thing, so I don't need the top anymore because now I want to focus on these 3 triangles. Okay, so obviously there's 3 right triangles. So one theorem that I could use when you have a right triangle is Pythagoras theorem, right? So we use right away, I'm going to use Pythagoras theorem. And what do we find? So sine this one squared plus this one squared equals this one squared. So the sine of x, so squared, plus the cosine of x squared equals 1 squared, which is 1. So sine squared plus cos squared equals 1, thanks to Pythagoras. Okay, so I think you knew this before. You've seen this one before, right? Right, everybody knows this identity. Okay, so that's where it's from. Okay, so it's from just the fact that it's a right triangle, okay, in the Euclid circle. Then let's do this one here. So 1 squared plus tangent squared equals secant squared. So that's easy also. So 1 plus tangent squared x equals secant squared x. And in this one also, 1 plus cotangent squared equals cosecant squared. So 1 plus the cotangent squared equals to the cosecant squared. Are there any questions? Okay, if there's no questions, I'm going to move on. Okay, so I left some space here because there's more identities that I'm going to figure out from these three triangles. Okay, so before that, I want you to notice something. The three triangles here, they both have two angles in common, right? There's the x and the x, 90 degrees, 90 degrees. So obviously, since the sum of the angles of a triangle is 180, the other angle is also the same. And so these two triangles are called what? Angle, angle. How do you call two triangles that have the same corresponding angles?
Equilateral triangle.
What did you say? What did you call it?
Equilateral.
Nope. An equilateral triangle is if it has all its angles the same or all its sides the same. But two triangles, when you compare them, if they have two angles, two corresponding angles that are the same or they're congruent, okay, we call them what? These two triangles. You probably did this in high school when you had angle, angle, side, and all that stuff. Nope, not isometric.
I think in French it was called équilatéral.
No, it's not called equilateral in French. Proportional, no.
Yeah,
Okay.
similar.
Yeah, very good. So I saw semblable here. I saw semblable, so semblable is good, similar is good. Okay, so two triangles are similar if you remember you have three cases for two triangles to be similar is if it was angle, angle, side, or side, side. Okay, so if the sides are proportional or if the angles are congruent. Okay, so in this case, all three triangles are similar. So I'm going to write this down. All three triangles. I'm sorry, I'm going to write a bit smaller. Can you see or it's blurry? Can you see?
Yes.
Okay. Are similar. Therefore, corresponding sides are proportional. Okay, so it means that if I start dividing corresponding sides, the ratio will be maintained. Okay, is this okay? Do you understand this sentence? Okay, so let's compare the second triangle with the first one. Okay, and see what we could conclude from that. So, well, tangent side corresponds to the sine side here, and the 1 corresponds to the cos, and the secant corresponds to the 1. So if I do the divisions, the ratios are maintained. Okay, that's what it means to be proportional. So tangent x divided by sine x, I'm going to write this down. Okay, so tan x divided by sine x has to equal to 1 over cos x. Which means if I isolate the tangent, tangent is equal to sine x over cos x. So I think you've seen this before also, right? I think you know this identity. And let's do now secant x over 1. is equal to 1 over cos, which means that the secant of x is 1 over the cosine of x. This one also, I think you know. Okay, and the last two, I'm going to compare this triangle now with this one. So the cotangent over, so cotangent corresponds to what in this triangle?
Cosine.
Very nice. Okay, because the cotangent is between the x and the 90. So which one is between the x and the 90? It's cosine. Very nice. So these are the corresponding sides. So cotangent x over cosine of x is equal to 1 over sine, which means that the cotangent of x is cos x over sine x. Good. And then I'm going to do the same thing with the cosecant. So cosecant x over 1 is equal to 1 over sine, which means that the cosecant is 1 over sine x. There you go. Okay, so 1, 2, 3, 4, 5, 6, 7 very important identities. Okay, they're the basic ones for trig. Any questions before I go further? Okay. Can I change paper? Okay, I'm going to take this out and I'm going to show you two more identities, okay, before I come back to the calculus part. Because these are two identities we're going to use. So two more identities. Okay, so the first one is that the sine of the sum of two angles, so A plus B, equals, so the sine of A times the cos of B plus the sine of B times the cos of A. Okay, so this is an identity. And another one, which is the cosine of the sum of angles, is cos A cos B minus sine A sine B. Okay, so these ones are important, we're going to use them. Okay, so of course we could prove them, okay, but it's going to take us maybe half an hour. Okay, and okay, I'm going to spare you. Okay, if it was a high school class, I would do it, but okay, I'm just going to prove basically the everything that relates to calculus. Okay, for now. If you need, you let me know. I'll do it for you after. Okay, so from here, if it was sine of 2x, so in other words, sine of x plus x, what will happen? Right? If the A is x and the B is x, then it will be sine x cos x plus sine x cos x. So it would just be 2 times sine x cos x. Okay? That's a special case of the one above. Okay, it's the case where the A and B are the same. Okay, same here. Cos of 2x, which is cos of x plus x. So it would be cos x minus sine x, which is cos squared x minus sine squared x. Okay, any questions? Okay, just one little note on notation. When you write sine squared x, this means same thing as sine x, like this, squared. That's what it means. Okay, we write it this way because we don't want to have to put brackets every time. Okay, so we put the 2 on the sign. Okay, that's what it means. Okay, we don't put it at the end because or else you would think that it's sine of x2, and that's not the same thing. Okay, you would think that the 2 is just on the x. So when we put it like this, the 2 on the sign, it means exactly this. It means sine x. This is the same thing as, if you want, sine x times sine x. Okay, same thing. Okay, just a little note for notation, and same thing for the cosine, tangent, secant, for all functions, all trig functions, that's the notation. Okay, so when you see sine cubed, it means sine cubed of x means sine x, all of that part. Are there any questions? Okay. Question, I'm gonna move on. Let's go back to calculus now, okay?
Sorry, I have a question.
Go ahead.
Sine square x and sine x square, are they the same?
Oh, that's what I just said, okay? I'll explain to you in a second. I don't know who's asking the question.
It's Daniel.
Okay, so be careful to answer your question. Okay, so sine, right here to answer your question, sine squared x. Okay, well, I don't know why I put the bracket, but this is equal to sine x squared. But sine x2, this is sine of x times x. That's not the same thing. Do you understand the difference? No? Okay. You are answering? Did you understand or no?
Yes, thank you.
Okay, perfect. Okay, any other questions? All right, let's go. All right, let's go back to calculus here. So limits. So involving trigonometric functions. Okay, so two things you need to know. First is that the limit as x approaches 0 of sine x over x is going to be something. And second, the limit as x approaches 0 of 1 minus cos x over x will be something. Okay, so if I plug in 0 here, I get sine of 0, which is 0, over x, which is 0. So I'm going to get 0 over 0. Okay, but except there's no algebra you could do here. Okay, so I'm just going to have to state for you that this limit is equal to 1. Okay, and I want to prove it to you in the rest of the page. Okay, same here. 1 minus cos. So cos of 0 is 1. So 1 minus 1 is 0 on top. And at the bottom 0. So again, I have 0 over 0. Again, there's nothing to do here. So I just have to state for you that this is going to be 0. Okay, so these two you have to know. Okay, especially this one. This one you could deduct from this one easily. Okay, once you're comfortable with this. Okay, so let's show that this is true. So I'm going to write this down. So proof that the limit as x approaches 0 of sine x over x is equal to 1. Okay, that's what I want to show. Okay, so I'm going to need your concentration here because this is going to get a bit tricky. Okay, and so you have to follow me every step. Okay, if there's one step you don't understand, don't wait, don't hesitate, just ask. So I'm going to draw a unit circle. Okay, as usual. So I'm going to draw it here. Okay. Okay, so this is my unit circle. I'm not drawing the whole thing. I'm just drawing the part of it because everything is going to happen in this part. Okay, as you will see. So I'm going to draw an angle. I'm going to open an angle here. Let's say something like this. Okay, and I'm going to draw three triangles. Three regions. Okay, so first region will be this little triangle here. Okay, so this little triangle. Second region will be, I'm going to draw the tangent. And complete this right triangle all the way to the top of the tangent. Okay, so I see three regions here. First, this little triangle here. Second is this big triangle here. And the third is the sort of sector here, the slice, the pizza slice that you see here, which is exactly in between the two triangles. Okay, so let me just put some colors, okay, so that you could see. So let me put this one here in blue. So this little triangle here. Okay, then the big triangle here, I'm going to put it in green. Okay, and the sector, which is exactly in between the two, I'm going to put it in red. Is this clear? Okay. Let's see where we're going with this. So it is clear to me that the blue triangle is included inside the slice of pizza, right, the sector, which itself is included into the green triangle. Okay, this is clear for everyone, I guess. Okay, so let's draw it. Okay, so I'm just going to put this angle here. I'm going to call it X. Okay, and I'm going to draw the three regions here separately. Okay, just to see clearly. Okay, so let me just move up here. Here we go. Okay, let me draw the three triangles. All right, let me draw the three triangles. Or the three regions, I mean. Okay. Put the colors, the corresponding colors in a second. There we go. Okay, so this is my blue triangle right here. Okay, the green one. Okay, I see. Okay, and this is my red one. Any questions? Little diagram here. Okay. No questions? I will move on. But one thing that's for sure is that this region here is included in this region, which is included in this region. True? Like we see in the diagram. In other words, the area here will be smaller than the area here, which will be smaller than the area here. Okay, so let's put on all the values that we know here. So this is x, and this is x. This is 90 degrees. Okay, and now let's put on the measures, because now we know the measures in the circle. Okay, so give me measurements here, please. Okay, so I'm hoping that you could tell me. How much is the base here? Can you tell me?
1.
1.
Very nice. This is 1. Perfect. How much is the height? Because, all right, the area of the triangle is base times height divided by 2. So I need the height here. The altitude measures how much? What's the height here? Could you tell me?
Isn't the sine of x?
Very nice. What you're asking, you have to be sure, right? Because here, you're right. If I go into my triangle here, the height will be right here, which is exactly the value of the sine of x, right? It's the y component of this point. Very nice. Okay, so this here is sine x. So I could find the area here. Base times height divided by 2. So 1 times sine x divided by 2. Perfect. Any questions? Good. Let's go with the green triangle. So how much is the base?
1.
1.
1. Still 1. And how much is the height?
Tan of x.
Very nice. Tan of x. Perfect. Okay, so I'm going to write the area here. 1 times tangent of x divided by 2. Any questions until here? Good. So now we need to find the area of this one here. Okay, so this one's a bit trickier. How much does this measure? From here to here is how much?
1.
1. Here. How much is this one?
1.
1, of course, it's a radius as well. Okay, so I need to find the area of a sector. Do you remember how to find the area of a sector from high school? Do you remember this? This is something you should have done in grade 8 or something. Okay, so let's go back. Let's open just a little side note here. Okay, I hope I could fit it in here. Okay. Okay, I'll try to fit it in here, in this little box. So, area of a sector. Okay, so I don't know if you remember, but to find the area of a sector, you would do the central angle divided by 360 equals to the area divided by the total area of the disk. Okay, so I'm gonna write this down. So central angle divided by 360 degrees, which is, we're a bit bigger, so we don't use angle, degrees anymore. We're going to use radians. So 360 degrees, how many radians?
2 radians, or 2 pi.
2 pi radians equals to the area of sector. I'm sorry if it's a bit small. Divided by the total area of the circle, which is pi r squared. Okay, this is a formula to find either the central angle or the area of a sector, depending on what they give you. Okay, or the radius or whatever. Okay, so in our case, what do we have? In our case, we have the central angle is x, over 2 pi equals the area of the sector, which I'm going to call here A for the area, okay, so which is equal to A over pi r squared, but the radius here is 1. True? Okay, so the radius is 1, so it's just A over pi. So now I could isolate A. So what's my area? Well, cross out the pi's and you're left with x over 2. And so I found the area of the sector is exactly x divided by 2. Okay, any questions until here? Can you see this or it's too small? Can you see? Is it blurry or it's okay? Yeah, it's okay?
It's fine.
Good.
Okay, good. So let's continue now from here. We're almost done. As you see, there's not much space left in the sheet, right? So I have to fit everything in here. So chances are I'm going to make it. Okay, do you understand this big inequality that I just created here? Okay, good. No questions means you're okay. So what I'm going to do now is I'm going to work some algebra. Okay, I'm going to work it out. So I will multiply everything here by 2 so that I can get rid of the denominators. Okay, so what's left? So here I have just sine x. Smaller than or equal to, here I just have x. Smaller than or equal to, and here I have just tangent x, right? Because the 2's cancel. And tangent is what? Tangent, we know it's sine x over cos x. Any questions on this step? Good? All right. Now, I see a sine x here, I see a sine x here, so I'm going to divide everything, all 3 parts, by the sine of x. Okay, what's left on the left side? It's just sine x divided by sine x is just 1. Smaller than or equal to. So here I have x divided by sine x. And then here, smaller than or equal to, sine x cancels, so I have just 1 over the cosine of x. Okay. So there's just one thing I have to specify here is that I divided by sine x, and I don't know if the sine x is positive or negative, because if it's negative, I would have to change the order of the inequality. Okay, but we should do both cases if it's positive or negative. But let's leave it for now because you'll see that they won't change anything. Okay? What I'm going to do now is I'm going to flip everything. So I'm going to flip this, flip this, flip this. So this becomes 1. This becomes cos. And this becomes sine x over x. Okay? And now I for sure need to flip the signs. Okay? If I flipped everything, the signs flip as well. Okay, so I just showed that the sine x over x is always, always, always included between 1 and the cos of x. I just showed this. For any value of x, this is between these 2 values. Okay? So if x is very, very, very small, well, this inequality will still hold. And so I could evaluate the limit on each side here. So that's what I'm going to do. I'm going to take the limit as x approaches 0 here, the limit as x approaches 0 here, and the limit as x approaches 0 there. And then I'm going to calculate things. This is how much? Well, as x approaches 0 of 1, well, that's just 1. And this is how much? When x approaches 0 of cos, so cos of 0 is also 1. So I just showed that this limit here, as x approaches 0 of sine x over x, is included between 1 and 1. I just showed that. So it has no other choice but to be 1, right? If it's between 1 and 1, then it's 1. There's no choice. There's nowhere to go. Okay, so we'll write here the limit as x approaches 0 of sine x over x is equal to 1. And I just showed what I wanted to prove. Okay, this is called, this process here of strangling a value or squeezing it. Okay, this is called the squeeze theorem. Okay, so this here, the fact that I managed to squeeze it, this is called the squeeze theorem. Okay, you're going to see this a lot. And that's the proof that the sine x over x, the sine of x over x, as x approaches 0, this limit is 1. Are there any questions? Okay, so this is probably the most difficult thing we had to do this semester so far.
Can you just explain the last two steps?
The last two steps.
Where you put the limits.
So when I took the limit,
Yeah, when you put the limit. Yeah.
okay, so here you're okay.
Yes.
Okay, so what this tells me is that x, well, here also, okay, before the limit, the sine x over x is between 1 and cos. Okay, okay?
Yes.
Sure?
Yeah.
Okay, so what I'm saying here is that the sine of x over x is always between cos of x and 1, always, no matter what the x is. So if x is 20, it will be good. If x is pi over 6, it'll be good. If x is anything, it'll be between 1 and this. Well, obviously, it cannot exceed 1. No, sorry, I'm sorry. Forget what I just said. I thought it was a sign. Okay, so this value, this value will never exceed 1. Sine x over x will never exceed 1. Okay, and it will never be less than the cos of x. Yeah, this we showed until here. Now, since it works for every value of x, then if x is approaching 0, also it works. So I could, nobody stops me from taking the limit here, limit here, limit here, and it still holds. Good?
Mm-hmm.
Okay, so now this, I don't know what that is. This is what I'm looking for. But I know that this is 1, because if you plug in 0 here, you get 1. And this is 1, obviously, it's just 1. So I just showed that this limit is between 1 and 1. So it has to be 1.
Okay, thank you.
Understand? There's no other, it cannot be 1.5, no, it has to be between 1 and 1. Okay, so let's apply this before going to proving the last one. Okay, let's just do some applications, some examples. Okay, there's quite a few of them to do. Okay, different cases. Let's start with the easy ones. Okay. So, examples. So evaluate the limit. So first one. So I'm going to do the first one. Okay. limit as x approaches 0 of sine of 2x divided by 3x. Okay, so here's an example. Okay, so as usual, I plug in the 0 inside, just like every limit. So sine of 0 is 0, and 3 times 0 is 0, so I still get my undetermined form. Okay, except that I have no algebra to do here. There's no factoring, there's no rationalizing, nothing, long division, nothing I could do. The only thing I can rely on is the theorem I just showed you. Okay, so this is how I'm going to do it. Equals to limit as x approaches 0 sine 2x over. So now the 3, so x on the bottom, but the 3 does not depend on the x, so I could extract it out of the limit. So this is like 1/3. Okay, I'm going to write down the properties of limits soon. Okay, once we get used to how it works. Okay, you'll understand the properties. This is a linear property that I can extract a constant out of the limit. Okay, so we're almost done. So I have sine 2x over x. Except I cannot say that this is 1 because, right, my theorem tells me, if you go back, it has to be, as you see here, it has to be sine x over x, not sine 2x over x. Okay, so these two values, this, the x here and the x here, have to be the same. Okay, this has to be the same, which is not the case here. This is not the same. Okay, so how do I make it the same? Okay, so what's inside the sine? I cannot work with that. This is trapped inside the sine. It's in another world. I cannot touch. This one I could touch. So this I will multiply by 2. And so I have to multiply on 2 on top as well. Okay, whatever you do on the bottom, you do on top. And so equals 2. And now the 2, this is a constant. I could pull it out of the limit. So it becomes 2/3 times limit as x approaches 0. And here I have sine 2x over 2x. Are you with me? Okay, so now I'm okay. Because now I have what? I have sine of something over that same thing. And they're both going to 0. So now I could confidently state that this is 1. According to my theorem. Okay?
Yeah, but why did it become like 2/3?
This one here,
Yeah.
1/3, you understand?
Uh-huh.
Okay, so the 2, where it comes from, is from this guy.
Okay, so if we multiply by 2, it's like 2 everywhere.
I pull it outside, I factor it.
Oh.
I factor it out.
Okay.
Okay? And that's what I'm left with. I just want to be able to recognize this form. Okay, every purpose of what I'm doing in these types of exercise is recognizing this form because this simplifies to 1. So that's what I have to aim for. Good? Try one. Okay, try one. I'm going to leave this in front of you. Okay, I'll leave the first one here. Okay, so try one. Let's try one right here. Number 2, right next to it. So they made the exact same type of question, just for you to get the hang of this. 5x over 7x. Okay. Go for it. The first thing we do is we check that it's 0 over 0. Perfect. 0 over 0. And so equal the exact same thing as before. Pull out the 1 over 7 times sine 5x. Oops, I forgot to write limit. Limit x approaches 0 sine 5x over x equals 1 over 7. And so I'm going to pull out, I'm going to times 5, sorry. Times 5 on the bottom, times 5 on top. And so I'm going to pull out 5. 5 over 7 times limit x approaches 0 of sine 5x over 5x, and now this, perfect, this is 1. Okay, and so I get 5 over 7, perfect. Okay. Any questions? Okay. Okay, let's go another one. Number 3. Limit as x approaches to 0 of, so let's complicate things a bit. Sine squared of 3x divided by 4x2. Okay, so first thing you do, as usual, you check sine of 0 is 0 over 4 times 0 is 0, perfect. And let's go. So now you have to be careful here. So equals, so I'm going to pull out, as usual, a quarter, like before. Nobody stops me from doing this. And now I have sine squared of 3x over x2. Okay? So far, so good? Okay. So now I have the square that's bothering me. Okay? So this is what I'm going to do. 1/4 limit x approaches 0. I'm going to rewrite it like this. Sine 3x over x, all this squared. This means the same thing. Okay, you get it? And now I'm going to put the limit inside. Okay, so the limit has a free pass to go anywhere it wants. Okay, now once, sorry, it's crooked. Now once I'm inside the limit, or once I'm inside the squared, I could treat it as a regular limit. So I just multiply by 3, multiply by 3. Okay. And so I have 1/4. I could pull out the 3 out of the limit. 3 times limit as x approaches 0, and I have sine 3x over 3x squared. Oh, and now I recognize that this is 1. Okay, so what am I left with? Well, 1/4 times, this is 3 times 1, this is 3. 3 squared is 9, so my answer is 9 over 4. Do you understand?